There we go. All right, we're recording. Good deal. So yeah, in our last exciting computer architecture class, we were studying information about how to do homework number 6 on software optimization, and we talked about loop fusion and loop rearrangement, refactoring of the code, and how we can test the code. And homework 6 is due at the end of the day on Thursday, this coming Thursday. And I was wondering if there were any questions about homework 6. Really? No questions? Well, that's all right then. I can, I have a nice presentation we can use. And this is something that I'd been sort of mucking about with a little bit. There's a nice pipelining lecture in here, but I'm not going to go through the PowerPoint death march on this and take you through the whole thing one PowerPoint slide at a time, because I feel that's a little counterproductive. Instead, what I'm going to do is zip over to, there's a couple of interesting things that are, yes? Was there a question? So in our last class, we were talking about superscalar pipelines, and I thought this was a really nice picture, and we could take ourselves through it a little bit. I had said there's an instruction fetch, an instruction decode, an instruction execute, a memory access, and then a write back. And these things represent various stages in the CPU. So the CPU is essentially going to use a register called the program counter. And the program counter, which you can see here as PC, is being used as an index into what effectively looks like a big array of memory. And what it does is it uses the program counter to act sort of like on your finger pointing at the next operational code or op code. And what it does is it goes to memory with the program counter, and then it assigns the instruction register with the next program counter opcode. And then it advances the program counter by however many bytes it takes to go past the opcode and the, I'll say the data that may be next to the opcode. So that's what an instruction fetch is doing. It takes a memory access in which to do it. And in here, what you can see is we've got an address register, that's your program counter. We got the memory it has to access, an instruction register that gets instantiated. And then here's this adder, and it's being incremented by 4 bytes. And it's going to go through and advance the program counter. The program counter here goes through a multiplexer and feeds back into an address to go and get the next instruction. And that'll work unless the program counter gives you an instruction that requires you to jump to some non-local or non-sequential address. So then we've got to do the instruction decode. And the instruction decode basically goes into the instruction register, and it does what's called a dispatch. And if you were a programmer and you had to write code for that, it would be looking very similar to a case statement. You would switch on the opcode, and if the opcode's a load, you do the load thing. If it's a store, you do the store thing. If it's an add, you do the add thing, etc. And you would have to have a case for every single opcode. And if there was 128 different opcodes, you'd have 128 different cases. And any compiler worth its salt would convert that switch statement into a computed goto, and it would basically make a jump table out of it. But if you were going to be a finite state machine digital design student, you would go and you would create a finite state machine that would essentially jump to the different states based on the opcode's value. And so that's a that's what's represented here by this dispatch right in here. So that's a decode. And then if it has to do something like an add, it can take the output and from this register and put it into the ALU. So if you want to add 10 to the accumulator, the ALU can do that for you. And then that's called the execute phase. And we do an address calculation based on the output of the branch. If there is a branch instruction, if it says jump, it'll jump. If it says branch if not equal to 0, it'll branch to whatever, and then goes and changes the program counter. And then the ALU has to do a write back of the output from your operation. And so it takes this data, writes it out to the memory, and then we can proceed to do some sort of lookup if needed, and we can put that into the register file as well. So that's a brief explanation of the steps needed. And these are the 5 steps of what's called the MIPS architecture, which is a reduced instruction set computer. Very similar to ARM. And this is the same thing, I think. So now we can see the big dispatch down and through here. There's the branch, the jump, some sort of a load, register to register operation, indexed register operations, some write back instructions, all based on the type of opcode or operational code that you're fetching. Let's see if there's anything else in here we need to think about. All right, so now we can visualize the pipeline. Instruction fetch, instruction decode, instruction execute, say instruction write back. There's a way in which you can overlap this stuff. And this represents a kind of concurrency, which is different from the sort of parallelism that we might hope to achieve if we were trying to write parallel programs. Here we have the pipeline creating concurrency as though it were an assembly line with workers where instruction fetch, once it's empty, will go and proceed to fetch the next instruction. So this is kind of a better diagram than I could have drawn on the board. So we've seen this before in sort of the abbreviated version when I sketched it on the board, but they just made a really nice picture out of it here. So that's kind of nice. Let's see now. So limits to pipelining. If you have an instruction miss, you depend on the prior instruction coming into the pipeline. If you miss the that next instruction for whatever reason, the pipeline will empty, and that will harm your overall throughput. Let's see, one memory port structural hazards. I think that's too much detail by half, so I'm not going to go too deep into that. I just like the pictures, you know. If I sat here and read through all these slides, I think you guys would be like a crowd of angry peasants carrying torches into the dean's office going, Professor Lyon is torturing us with PowerPoint slides. What's the matter with him? So I'm just going to sort of get through the concepts. I think that's enough. Let's see if there's any other. This doesn't look like it's adding very much to the discussion. Yeah, all right. So here's the programmers, from the programmer's point of view. When you execute an instruction, you can either have what's called a caught exception or a runtime exception. In the case of a caught exception, you would surround the code with a try-catch block. And if it was some operating system invocation that attempts to do I/O to a file, maybe you got an I/O exception at runtime, you could try and catch that and maybe handle it accordingly. Similarly, you could generate your own exception. You might say, oh, I'm going to decode this credit card in my business logic, and the business logic tells me the credit card's not valid because it doesn't have 16 digits, and it throws a credit card exception. So my code can then proceed to handle that and say, hey, that's not a valid credit card number, type in something else. So then there's this other kind of exception. We're going to call it the runtime exception. And we don't have to try and catch it. It's implicit. And what you can do is something you're really not supposed to do, like, I don't know, divide by 0. If you divide by 0, that gives you an arithmetic exception at runtime. You don't have to try and catch every single division to have an exception thrown when you start dividing by 0. It makes the operation illegal. And it throws you into, it throws your thread into a separate path that then requires you do something, right? Somebody said, enter in the bottom of the divisor, and you entered in 0. Throws an exception and says, okay, you can't put 0 in there because you're dividing by 0. And so then you can try and handle it somehow. Or if you don't handle it properly, it stops the main thread of execution and your program is dead in its tracks and it just crashes. And someone says, type in, your date of birth, and you typed in 0, and somehow it's dividing through by that and comes out and says, bleh. And there's not a whole lot you can do about it because you don't know how to deal with dividing by 0. And neither do I. So that's that's sort of my thing about, these slides. I don't like to go through a bunch of slides, but sometimes I like the pictures. So that was my shtick. So have you given any thought about homework 6? Any questions about homework 6? Shall we just kind of look at the questions and see if there's any questions? Kind of go through it. Multi-threading provides us with a lower overhead when switching context and multitasking. True or false? No idea.
Yes, it's true.
Yeah, that's true. That's true. Let's try another one. Let's see. Any questions about why that's true? No. Okay. Let's try another one. Multitasking has the advantage of protecting memory versus multi-threading, which requires a shared memory model. Requires it. Is that true? Does it require it?
It's true.
It is true. That is true. It's true. And in fact, that's the advantage and disadvantage of multi-threading. It's not protected memory, but on the other hand, because it's not protected memory, you can switch context quick. So that's nice. How about this? In Java, when we create a new thread, the thread begins to run. Is it true?
False.
It's false.
That's false. It's just ready. It's ready to run, but it doesn't run till the scheduler gets to it. And plus, you have to say start, right? Just creating new instances doesn't do anything. You got to hit start on that. And let's see, threads support concurrent programming, but a thread is not necessarily going to give us true concurrency. Does that sound true? What's true concurrency? I don't understand. Can somebody please explain what is concurrency? What does it mean to be a concurrent programmer? Does that mean I program at the same time as somebody else? Is that a concurrent programmer? Nobody's chiming in on this one. So concurrency, true concurrency, is when two things happen at the same time. And when you do threading, or multitasking for that matter, you don't have two things happening at the same time. You're still switching from one thing to the other. If you wanted it to two things to happen at the same time, you might consider something like pipelining, like in a superscalar machine, or parallel programming, where you can get two different programs running on two different computers at the same time, or two different cores even. That'd be all right. So here's another one. multiple processes can only be realized with multiple tasks. Often this is implemented with multiple Java virtual machines. Multiple processes can only be realized with multiple tasks. So I guess, and what's a process? Is that different from a thread? Is a task different from a thread? Well, let's have a look. Okay, I'm gonna. Here comes my multitasking machine. Look at all of these things that are running. They're all running at the same time. Now let's quit out of the preview thing, and you can see it's gone now. And let's quit out of like the QuickTime thing, and you can see that's gone now. I won't save that. And then let's see. Let's quit out of the Blackboard thing. So that's going now. So this is looking like a collection of applications for sure. But in fact, it's the moral equivalent of the Windows Task Manager, only it's running on a Mac, for whatever that's worth. So you can see when I quit out of these applications, these things are quitting, right? So then is that multi-threading or is it multitasking? You tell me. Anybody have any idea what that is?
That is multitasking.
That's multitasking, and that's different from multi-threading, right? So one of the things I might like to do is, I mean, here's a great example. I was getting this from this morning, right? I have a little 8-bit toaster controller called Arduino Uno. Arduino Uno does not have a multitasking operating system. In fact, Arduino Uno does not have an operating system. This is sort of a big deal. If you don't have an operating system, what are you supposed to do about it, right? I mean, there's only so much you can do, and then what? You're stuck. And what are you going to do? So if you can't do multitasking, how do I do two things at once? And the answer is use interrupts, right? So here we have a timer. It says every 100 microseconds, I'll sample my DAC. So it attaches the interrupt, and we know every 100 microseconds, this thing is going to run. It's going to call DAC sample, whatever that does. Takes in some kind of a sine wave, outputs out to the DAC, and we say no interrupts during that period of time. So what happens is whatever was going on in the CPU, it gets pushed onto the stack and saved. All the registers, everything gets saved. Then it jumps to this interrupt. It gets no interrupts, which means nothing can interrupt it as it runs, outputs to the DAC, then turns the interrupts back on, and then it goes back to whatever it was doing. And then we have, sort of this other thing. It says init ADC, init the analog to digital converter, which apparently is a lower priority thing. So when we init that, we start an interrupt that occurs every time it's done converting. So we enable interrupts, and when it's done with its conversion, because it's got an automatic trigger to keep converting after it's done, it'll proceed to call interrupt service routine ADC vector. So what's this doing? Well, assuming it's not interrupting the DAC, and we know it can't because it says no interrupts, when this is done converting, it's going to go and sample the analog to digital converter. So it's like another task operating in the background. Everybody's sharing memory. Maybe it's more like a thread, but a real-time thread, because the other thing was operating in every 100 microseconds. This thing operates whenever it's done. It's free running. And then in the foreground, I got a loop. And the loop says, oh, let's print out conversion times. Right? So now when I go in and I take a look at sort of the serial monitor, I can see conversion times are being printed whenever they get printed. Sending things out to the DAC takes like 8 microseconds. which is not exactly an accurate thing because it's plus or minus 4 microseconds, so it could be off. But you can see it's printing kind of slowly, and yet the DAC continues to run in real time. In fact, we can hear it. I'll say at the end of that sentence, I hope. And what it's doing, it's busy taking a sine wave and sending it out to the speaker. And it does that in real time. And when I say in real time, in every 100 microsecond interval, it takes 8 microseconds out of its life to send out a sample to the speaker, then allows you to go back and do whatever it was you were doing. So is it true concurrency? It's like making sausages. Once you see how they're made, you don't want to eat any, right? So it's not true concurrency, right? It's being interrupted. And it's trying, is it multitasking? No, well, they're all sharing memory, so that's not true. Is it multi-threading? Oh, it's not that either. It's real-time, interrupt-driven programming that's essentially saying, look, there are certain things I have to get done in a certain amount of time, and it's kind of simulating multi-threading, but in a way, because it's got like this real-time thing going on, it's doing something that most multi-threading systems couldn't do. Because it's telling you, I'm going to do a conversion every 100 microseconds, and that conversion will take 8 microseconds. And I have to do it that way, or else I'm not going to have a stable sine wave on output, you know. And you could print whatever you want. I mean, here I'm printing Mickey Mouse as my hero. You could print out the Gutenberg Bible. It's all being interrupted during the printing process, and we know the printing takes a long time, at least in part because we're going at a reasonably slow speed. 9600 baud is pretty slow for USB. So that's a, so here comes the question. Multiple processes can only be realized with multiple tasks, and this is implemented with often this is implemented with multiple Java virtual machines. And what do you guys think? Well, the answer is that's true, right? Because the tasks are going to, the multitasking system allows us to manage multiple processes. And here's like, for example, Keynote is another process. So in principle, I could go to Keynote. It's got its own memory. It's doing its own thing. And here in the Keynote display, and this is kind of interesting because we were alluding to this last time, we can see the difference between the different DDR RAMs. DDR4 is like double the speed of DDR3 in terms of transfers per second. So it's kind of an interesting thing when you look at the comparisons and how fast these things are. DDR2 is generally, you know, half as fast as DDR3, which is half as fast as DDR4. Presumably there'll be a DDR8 one day. And effectively the number of megabytes per second for transfers is going to double every time we go to a new family of DDR, which is kind of neat. So let's take a look at question 6. Each thread can be scheduled on a different CPU core or use the time slicing on a single hardware processor or time slicing on many hardware processors. Every Java virtual machine implementation can do it a different way. Is that true or false?
That's true.
Yeah, that is true. That is true. We don't know very much about whether or not we have green threads or native threads. So then here's another one. Each thread is associated with an instance of the class thread. I wonder if it would be educational for us to just kind of quickly see how to do something like multi-threading. It's not particularly difficult. I think I've got some nice examples in chapter 13 of my book. Here's a nice one. I could probably just run it and see if it works. This will run a clock in a thread, and there it goes. And now you can sort of see there are these different threads, and they're updating these clock labels in different places. And they're doing it in their own time. So that multiple threads are running at the same time here. And this is, it says there's 400 of them. God, what are we doing with 400 copies of the clock? Here's one that I usually keep running on my screen. It's right there. So I always keep this up on a monitor that's out of sight, so I can just kind of take a look at what's going on. And that's a little Java program that simulates a multi-segment LED display. I thought that was pretty cool. Also runs in a thread, runs in the background. And so then the question is, how many threads can I display? And here I'm doing 400, and each one is running as a separate digital clock label. And if we want to, we can take a look. And we've created this thing called the run job, which is a thread that runs every so many seconds. And then all it does is it updates its label, changes the label every so many seconds with a new instance of the date, which it converts to a string. So if you look at something like the run job, what that does is it gives you a runnable interface. So that means you have to implement the run method. And it allows you to set priorities and has its own little thread. And it runs the runnable thing, which is the run job itself, which implements runnable. So all you have to do is supply an implementation of the run command. And you can start and stop these things, and you can set them up as daemons and change their priorities and all this other stuff. Just a convenient way to create a thread. So a run job has a thread in it, which is kind of neat. And you can define how many times it runs, whether it continues to run after the main quits, define its priority, define whether it waits or not before it starts, stuff like this. Run job. So it's really just, I don't know, eye candy for a thread. Let's quit out of this. Got too many things running. So here's loop fission and loop fusion. We kind of covered that last time. Let's see if we can answer it. In multiple core processors, two or more processing elements may work concurrently. Is that true or false? In multi-core processors, two or more processing elements are working concurrently. This is question 8 now. Anyone have any ideas?
It's true.
It's true. Yes, it is. And it's a compelling argument for loop splitting, right? Because if you needed to do these two things inside of the loop and you could split it, maybe it would automatically be dispatched to two different cores, in which case the two different for loops could run concurrently on two different processors. Here's loop jamming. And it says here, loop fusion does not always improve runtime speed. So what are we doing here? We're taking two separate loops like this one, which adds 1 to every element in the array, and this one, which adds 2 to every element in another array, and we put them together. Why is that a bad idea? Now we just need one loop. What's wrong with that? I like that. It looks simpler to me. What could possibly be wrong? Any idea? You're not allowed to sit like lumps on bumps. Why wouldn't I like the idea of taking these two separate for loops and combining them into a single for loop?
It
Well,
doesn't take advantage of the principle of locality.
there you go. That's exactly right. So the principle of locality tells us we want to stay within the array, which is presumably being accessed sequentially, and that's going to end up in cache, and we're going to be able to do that in an accelerated manner. Moreover, by splitting these two things, they could end up being executed in two separate cores. So that's kind of nice. So here's locality of reference, also known as the principle of locality. And this is your basic question. In computing, a pipeline known as a data pipeline is a set of data processing elements connected in series where the output of one element is the input of the next element. Pipeline. So let's have an example. Let's do something real with it. So let's create cat, which is a thing that cat concatenates, and we'll take readme .txt, and we will pipe it into word count, and then word count will say how many lines in that file, and it'll say 1. So apparently readme is not very long, but there it is. So if I did the same thing, let's say with a binary file, I don't know if that's a good idea, but here, cat lecture 16 on memory hierarchy, and we'll put it into word count minus L. That might not work very well. Oh, kind of did actually. So it gave us a number. Now the other thing we could do, and this probably will really break, is we can pipe it into more. So the output of the cat program is to list the data that is contained inside of the PowerPoint, and then here's the pipe, which takes that data and then pipes it into the more operation. That's probably going to make garbage because you're not supposed to be reading PowerPoints, although maybe it's educational. I don't know. Yeah, garbage. So that's not good. We don't like that. Garbage. Let's see if there's another good example we can do here. I suppose you said find dot. That's going to get all of the files in this directory. Let's pipe it into a grep on PPT. So now we'll find all the PowerPoint files. Then we're going to pipe it into more, and we'll be able to list them all one screenful at a time. So that's piping. And here we are looking at all the PowerPoint files, and every time we hit space, we're able to find anything with the word PPT in it. It may not be a PowerPoint file, because here we see some XML with PPT in it. And if we don't like that, well, then what we'll do is we'll say grep, and then put in quotes dot PPT, end quote, and make sure there's a dot PPT in it. And so that's not doing so well, actually. That doesn't matter. You get the idea. So piping lets me take the output of one thing and put it into another. If I have a multi-processing environment with multiple cores, the piping essentially allows me to use one core do one thing while the other core does something else later in the pipe. So this is this enables a kind of concurrency with pipelining, instruction level concurrency, or data level concurrency. So that's true too. Let's take a look at question 11. And now here's the sort of summary of the complex slide that we saw from before. Mem is a memory access. Let's see what we knew. Write back, memory, execute, instruction decode, and instruction fetch. So in a classic RISC pipeline, mem is equal to memory access. Does that sound true?
Yes.
Yes, it is. So then here comes question 12. Here's a simple finite state machine to implement some sort of RISC CPU. So instruction fetches are happening here. And it wants, what's the question here? What's the question? The following is a simple finite state machine to implement a RISC CPU. Is that true or false? So here's an instruction for load, for store, for add, for branch. That's basically all you need for an instruction decode. All you have to do is dispatch on one of the 4 instructions, and then you can do whatever it is you have to do in order to execute the instructions. And that's a simple CPU. Doesn't do much, but that's it. So that's true. Let's look at this other question here. I'd like to kind of go through these, at least to make sure that you guys are on board with it. So here's the loop unrolling idea. Let's see if we can take a look at it. Here's the for loop. You guys ever use VHDL? In VHDL, it would unroll this for loop. It would list this printf statement 5 times. And if it was, you know, for I equals 0 to 5,000, it would list the printf statement 5,000 times. The only way around it in behavioral VHDL is to write something like a while loop and just, or repeat until, and just keep doing the same thing until some condition occurs. So here's the unrolling, right? That's clear. That's, what is that, 5 printfs, something like this. So, so what was the question then? Loop unrolling increases program speed by eliminating the control loop. So here's a control loop, right? What's he doing? He's incrementing I. He's testing to see if it's greater than 5. And so, you know, that's true because you no longer have to do those things. There's no more testing. There's no more incrementing. It just unrolled the whole thing. So presumably that's faster. Maybe. And then we talked a little bit about row major and column major order. And I think that's pretty close to where we left off last time. Does that sound about right for everybody?
Yes.
Yeah. Okay. So here we can see it now in beautiful color. Excuse me while I move my mic. And this is looking like row major because it goes left to right, top to bottom, scan line order. And here is column major going top to bottom in a kind of sideways scan line order. So it says here in Java, should we always access arrays in row major order? Or we should always access arrays in row major order. Is that true or false?
False.
Yeah, that's false because Java language specification doesn't tell us if we're in row major or column major. Just doesn't tell us. So here is another image. This is looking more like a very colorful array of rows and columns. And here's how they're being stored. Is that being stored in row major or column major? Because it asks, right? The above image shows a row major ordering. Is that true?
Yes.
Yes, it is, right? Because it's the scan line order, left to right, top to bottom. So this is interesting to us because if we wanted to create a for loop that simulates 2-dimensional arrays, we could do it with an addition and a multiplication, which oddly enough is not expensive in modern CPUs. It can be done in a single CPU cycle. And so here's an example of what that might look like. You take the row number multiplied by the number of columns, and then you offset by the column number. And that simulates row major ordering using a 1-dimensional array and gives you this offset. So if you just increment rows and columns in this way, you can know that you must do the columns more frequently than the rows, and that'll keep things going sequentially. And so, am I simulating row major ordering here? I say yes. So let's do another one. Here's a for loop. I goes from 0 to 10. Another one from j equals 0 to 20. Here's I and j. Loop interchange starts with j going from 0 to 20 and then I going from 0 to 10. This will always result in an improved performance. Does that seem true? Why would loop interchange always result in an improved performance? It might result in an improved performance. Why would it always result in an improved performance? The answer is it wouldn't always necessarily do so because it violates the principle of locality. So you need to benchmark to be sure. If your benchmark shows the performance is improved, then maybe that's the way to go, at least for that platform. But as you change platforms, change virtual machines, maybe it won't help you. So here's another one. Using compiledjava.net. So here's a very interesting sort of idea. Online, you can go in here and take a look and see if this really works. Right? They're upgrading. Bummer. It no longer works. Gee. What a shame. I was relying on that. So here, in using compile.net, you used to be able to execute this program, but you can't anymore. And it says test column 1, test row, test col, test row. So here's test row, and it's looking to me like he's incrementing more frequently in the rows over and through here. And here's test column. And now he's incrementing more frequently in the columns over here. And then each time he's printing out the elapsed time, taking a snapshot since the beginning of the clock, which would be in 1971. So it's milliseconds since 1971. And he computes the elapsed time since then. And each time you do that, you can say, oh, this one's faster than the other one. And so here's the output. This is interesting because one is faster than the other by a lot. And that kind of makes it look like we have row major ordering. Is that true? And the answer is yes. Because we did row major ordering in the first, and then column major ordering in the second, and we wanted to run the benchmark to see which one was faster. So at the time I did this, when compiledjava.net was working, I was able to run this benchmark and test what the nature of the virtual machine was doing with regard to column major or row major. Probably could do the same thing with a Java virtual machine that I have handy here. I mean, that might be somewhat educational. Let's just take a quick look. We'll just grab the code and So that looks correct to me. Something bad happened. Oh. Looks like we lost some characters in there somewhere. There we go. So the same result, you know, one is faster than the other. Although both are a little bit faster than this web-based system. So that was pretty cool. Did everybody understand what I just did? I output this class file that contains the bytecodes when I did javac on the Java source file. And then I ran the bytecodes when I called the Java virtual machine and said, hello world. I hope that isn't too much Java for you guys. So then, let's see, that does our in the following code, test simulation. So now we're doing something here that looks like we're simulating a one-dimensional, well, we're using a one-dimensional array, but simulating a two-dimensional array. And we're incrementing j more frequently than we increment I. And looks like the number of elements in each row or column. The simulation of the two-dimensional array will be faster. So here's the two-dimensional array, and over in here is the simulation of the two-dimensional array. And if I'm right, the simulation of the two-dimensional array should be faster. Is that true? Any ideas? Can take a guess? Well, the answer is false. We don't know that. We have to benchmark it to be sure. So in other words, you have to run this code on your Java virtual machine to test it. And you might get different results if the sizes of the array are different. For all I know, they all fit in the cache that you've got on your CPU because they're small arrays. So that's, that's possible. Both could run at the same speed for all I know. And in fact, if you don't test it, you can't know. And in some cases, they might run at the same speed depending on how big they are. So here's question 20. Moving on, unless you guys have some questions. Let's see now. Loop invariant code consists of statements or expressions which can be moved outside the body of a loop without affecting the semantics of the program. So think sigma or integral where there are constants, and you move them outside of the integral because it's really independent of the integral. So calculations like this and calculations like that could be moved outside of the loop because they don't have anything to do with I. So these things, like the multiplications, that's like a constant. And this y plus z doesn't look like these are going to be changing either. So if you needed that, you could move that out x equals y plus z. Doesn't look like it's in the loop at all, actually. So here comes an interesting thing. The y plus z is moved out. The x squared is moved into an auxiliary variable. And now you can do something like this. And that's supposed to be faster. So this loop invariant code motion will always be done by hand, and will always be faster when done by hand. This is the big question. Always faster when done by hand. Does doing it by hand somehow make it faster? And the answer is no, it doesn't. Can you do it automatically? And the answer is yes, you can. Any compiler worth its salt will do this for you. But you got to be benchmarking the code to be sure. So compilers will recognize static code inside of a loop, and they'll move it out of the loop. So what do you think of that? That sort of covers homework 6. I mean, you guys have any questions about homework 6? So we had talked a little bit about this so-called memory hierarchy thing. See if I can get PowerPoint to open this. So here's an interesting question. Can memory make your computer faster? And the answer is yes, it may, especially if it's faster memory or if there's more memory and you become sort of short of memory. Everything can bog down if you don't have enough memory. It's sort of an important metric of performance, having enough memory in your system. And that's a funny thing because I noticed that whenever I shop for a computer, I never seem to have enough memory in the base computer. I'm always thinking, oh boy, they didn't make this with enough memory. And then I have to go out and take the DIMMs out of it and put in newer, denser DIMMs. Sort of a nuisance, really. So we've been talking a little bit about the cache. This is static memory that's high performance, low density, sitting next to or inside the CPU. And what we are looking to do is we're looking to use the principle of locality to fill that cache. We're attempting to pipeline so that things are in the cache. We're attempting to access banks of memory so that they get swapped into and out of the cache. And all of these things are forms of, I'll call it software optimization. Let's see if we can't advance this a little bit. Cache miss optimization studies. All right, so this is somebody who wanted to just study one thing. And if you do that, right, if you say, oh, let's just study this one thing, we'll talk about sparse matrices. It's possible to come up with all kinds of interesting generalizations about sparse matrices and how to do operations with them. A sparse matrix is a matrix that doesn't have a number at every element. You can see that by the names here, these are relatively old computers that we're describing, but it kind of doesn't matter. Let's see if we can find, okay, so this is interesting. So here's dynamic RAM. We know dynamic RAM is dynamic because we have to have a capacitor, and we also know that capacitors tend to leak. They leak with time. And what happens with the dynamic RAM is you have to refresh it in order to be able to allow it to maintain its charge. And we refresh the dynamic RAM by going from one row to the next and one column to the next and strobing a little energy in there to keep the capacitors charged. We don't have to do that with static RAM, because static RAM is using a flip-flop, and that flip-flop can maintain its state indefinitely without somebody coming in and refreshing it, but it doesn't have the same density as a bank of capacitors. Also, it has a much higher cost because of the number of different elements that's inside of the static RAM. Making a D flip-flop is not particularly cheap in comparison to, well, in comparison to capacitors. Then there's this thing called core. And this is a lousy picture. Core represents ferrite beads. There's an R, and this is a donut made out of iron, and there's a charging coil that's wrapped around it, and this is a sensing rod that goes through it. And when you sense the charge on the core donut, it collapses the magnetic flux on this little donut and gives you the charge as a readout. As a result of it being non-volatile, people can go back to old computers that have core, turn the computers on for the first time in decades, and they will have retained the program that was put on them initially. I went out to, well, the PDP-8 computers that I was using all had core. PDP-11 computers, some of them did too. Here's core memory. I think you should be able to just sort of see it there. That's what it looks like. It's wired by hand, believe it or not. So these little core donuts, and I think you can break this out and zoom in a little bit. There. And you can see the sense cables. See if I can zoom in. These are little core donuts. They're iron, and these wires go in, and they are threaded by hand. And boy, what a nightmare threading the core donuts must have been. When you read from them, you must immediately write back to the core, because reading from them, reading is destructive. Reading will take the data out of the core. But if you just let it sit there without power, it'll retain the the magnetic orientation on the cores, presumably indefinitely. Core memory. And look at the density here. This is 1,024 bits. It's not very dense. And it's not volatile RAM. That's not the other thing. It's almost like double EEPROM. I saw the Whirlwind core. This is at a museum out in the Massachusetts area near Boston, I think. And I think, yeah, these tubes are being used to access the core. Let's see if we can see the actual core itself. Yeah, there it is. You don't see the donuts as easily as you did in the last picture. But you can still find this out in the museum. This is the Whirlwind computer. Came out of MIT. It was not a product. It was not a production computer. It's more like a prototype. See if there's any more good pictures of core. Oh, and here's the core in a PDP-8. I guess that's all the pictures they have, but I like the fact that they had some nice pictures. It's good. It's good for you guys to see that stuff. Old computing. And here's the DRAM. Dynamic RAM needs the row address select and the column address select to keep the the capacitor's charged. So what you have is extra logic to do the RAS-CAS line pulses, and they go up and down the columns and up and down the rows, continuously recharging things at multi-millisecond intervals. Let's see, we already talked a little bit about double data RAM. That is a form of synchronous dynamic RAM. So there's a clock, but it's going on both the rising and falling edge of the clock. And we saw the speeds, the changes in speeds, I think. So that was good. I'm glad we went through that. Let's see if there's anything else in here we need to know. I don't care about Zen. So next thing up, I think we ought to think about is truly parallel programming. And in truly parallel programming, we want to think in terms of how we can proceed to get two things to happen at exactly the same time, and how we would do that in our programming environment. In order to get there, we have to know a little bit about networking. And so that leads me to the next question. Who here has had a basic networking course? Anybody have any networking background at all? Well, maybe what we'll do is we'll just do a brief intro then, since you guys might not have it. I mean, as it happens, there is a separate course in networking. But what I like to do is I like to take people through some of the basics of networking, and maybe the best way to do that is by introducing you to the network hierarchy. So what I'll do is I'll just kind of give you a quick picture / overview of networking. Let's see if we can do this one. So let's just skip ahead. I'm going to go into what's known as the OSI. I think they have it in here. Let's just do a quick SI enter. Maybe it's not in here. I thought it was in here. No, doesn't matter. We'll try it one more time and see if this is going to give us the data I was interested in. Yep, there it is. So OSI, Open Systems Interconnect Model, is a 7-layer model. It's part of the ISO standard, the International Standards Organization standard. And it comes in layers. And those layers, I'll just kind of outline them real quick for you in here. The layers of the OSI model. You're going to have the physical layer that deals primarily with moving energy from one point to another. There's going to be the data link layer. And in that, you're going to have packets. So if you think about point-to-point protocol, PPP over Ethernet, link access protocols, etc. That's what you find in the data link layer. Physical layer, you would see something like bits coming in, going in and coming out, just bits. And you can do that with any physical property such as RF or voltage, that is radio frequencies or voltage, or maybe light, fiber optics. How else would they do it? Then there's the network layer. That's where you might find something like Internet protocol. Then there's the transport layer. And that's where you might find transmission control protocol, which layered on top of IP becomes TCP/IP. Then comes the so-called session layer. And that's where we do things like security, like HTTPS, secure sockets, remote method invocation. Then comes the presentation layer. And that's where we might have things like HTTP. That's hypertext transfer protocol. We could have HTML being transmitted. We could use common gateway interface. What else would we do? Oh, we can translate from Big Iron, EBCDIC. And that's versus ASCII. So 2 ways to do encoding, for example. And then comes the application layer. And that's where you might have things like your browser or FTP or SSH or something else. I don't know what. How many layers is that? So that would be first layer. This is your second layer. Did I miss one? Third layer, fourth layer, fifth layer. Oops. Sixth layer. And that's the seventh layer. So those are the seven layers. And you can't really say that the modern TCP/IP networking makes these layers obsolete because you can relate these layers all to modern networking. I don't know why this is over here. It's doing what it wants to do. Oh well. Shift tab, does that? No luck. So that's a you can't stop it. Nice. So there are the layers. When we start doing network programming, what we're trying to do is do things like remote method invocation. So we're kind of in this just above the TCP/IP layer. And there are certain services which we can expect from each one of the layers, such as TCP/IP. What you would expect in here is a socket suite. And so you open up a socket to another machine, you can dump raw data into it, and it comes out the other side by virtue of the layers below it. So it ends up giving you security, and you effectively take advantage of this sort of thing. So you can go and in the background, do a remote method invocation, get an answer back later, and then go do remote method invocations on other machines and have a master-slave relationship with those machines. So session layer, that's also going to do things like login, security. Oh, I already wrote that. Secure sockets, security. So there's the physical layer. That's bits. Here's the data link layer using data link protocol data units, which is what they call it, but it's packets. Ethernet frames. Here's the network layer that does routing. So routing is an interesting function. Routing allows you to determine how to get from one point to another through a network that may do storage and forwarding. So this enables it enables, I'll say, internetworking as opposed to internet working with a capital I. Internetworking. So internetworking means I can go from your little local area network to my little local area network. That's not necessarily the same thing as going on the internet, although that's also possible with routing. Then there's the transport layer that does the flow control. So here in network layer land, you may or may not choose to use TCP on IP. IP is the network layer. TCP is the layer above. You could instead use something like UDP IP. And so you're still using IP, but now there's something else going on. Here, TCP guarantees that the data that you push into the socket will come out in the same order. UDP just takes little envelopes and dumps them into the mail, and they get there whenever they get there. So it's just like taking an envelope and, let's say, an encapsulation of your data, putting it into a single unit, and dropping it into the internet and hoping that it gets there at some point later. And then it's up to the application layer to reassemble these things. So let's see now. Here comes the session layer, and then the presentation layer. And we already talked about data format conversion. And finally, there's the application layer, file transfer, FTP, virtual terminals, SSH, electronic mail. Oh, that's a good one. So there's all kinds of interesting and wonderful layers there. And they have all these different interesting and wonderful features that they allow you to use to isolate the complexity from your code so that you can just assume that TCP IP will work. Open up an IP address, drop in some data, and know that it's going to come out the other side. And you're doing that because you're taking advantage of the layers and the services that they provide. And so with that knowledge about how the network, the computer network works, we can now proceed as programmers to take advantage of the network in order to do truly parallel computing. And that is an interesting thing. And unfortunately, we're out of time, so we'll have to talk about that next time. We're going to continue to go on this online format. I hope it's okay for you guys. Is everybody all right with the online format as it is?
Yeah.
Good, good. You know, if you have problems with it or something like that, you'll let me know. Shoot me an email or whatever, and I'll try and help you out. So we've got a homework due coming up Thursday, and you guys stay safe, and thanks a bunch for your attentions.
Professor, I have a question.
Yes, sir.
On the Blackboard page, there's a assignment. I was just kind of being nosy, and it was in like the gradebook section, and it was Computer Project 1, and it's due the 23rd, which is not coming up, but that's next Friday. But I haven't really seen or heard anything about it. I was just kind of curious what that was.
I have no idea. Where are we looking at?
So it wasn't like in here, but like if you go like in the My Grades section of Blackboard, and like you like go to look at your grades, it shows like a bunch of other assignments, and one of them is a computer project number 1.
Okay, this class had been taught by another instructor at one point. I think it was Dr. Belfidel, and I believe she had a bunch of old homeworks in here. And
yeah, there it is, the computer project 1. It's all the way up on top. Yeah.
Okay, and so this is not something I was planning to do.
Okay.
What is the story with that? I don't know. Let's say for the moment that I have no idea what this is, and I'm going to look into it. But thank you for bringing it to my attention. I wasn't planning on doing the homeworks that she had created and assigned.
Okay. All right.
Okay.
Thank you.
Thank you.
Thank
Have a good day, everybody.
Thank you, Professor.
Thank you.
Thank you.
Thank you.
Thank you.